Welcome to all of the attendees who are with us tonight and our panelists who are going to talk to us about the James Webb Space Telescope, the largest space observatory ever built. So we all are here because exploring the heavens is truly fascinating, captivating children and adults alike. The men and women who participate in space exploration fascinate us. The scientists who develop the technology that sends spacecraft and telescopes and people into space inspire us with awe. Science teaches us that some phenomena are better observed from space than from Earth, and that offers a perspective that we must apply to our human environment. Through the discoveries resulting from the James Webb Telescope and the efforts required to launch it and to maintain it, we will learn so much more about our solar system, our galaxy, and the mysteries of the universe beyond. So I'm delighted that you are with us tonight, and I want to introduce our truly distinguished panelists, Dr. Ed Belbruno and Dr. Marian Gidea from the Department of Mathematics at Yeshiva University. I just want to take a moment to say how proud we are of the mathematics department at Yeshiva University, made up of distinguished faculty who teach truly remarkable undergraduates, graduate students, and doctoral students. The caliber of this department is extraordinary, and we thank you, Dr. Gidea and Dr. Belbruno, for all your contributions. We want everyone to know this is only one expression of Yeshiva University's dominance, as we say, associated with the flagship Jewish university. So I would like to now, once again, thank you and turn this over to Ed Belbruno.
Thank you very much, Selma, and on behalf of myself and the panelists, would really like to thank you for the opportunity to have such an exciting event. And also, I do want to thank someone who put a lot of work into this, Kenny Almanzar, who had to put together a lot of logistics very quickly, and many other people involved in this. The title of this is Unlocking the Mysteries of the Universe, a pretty lofty title, but it's really about the James Webb Space Telescope. What is the James Webb Space Telescope? I want to keep it very simple. In short, it's a gigantic telescope. It's really large, but it's one of the flagships of NASA in their observatories. So the first one that we all know is the Hubble, which orbited pretty low to the Earth, a couple hundred miles up. And everybody has seen those incredible photos of the Hubble Space Telescope since the 1990s.
Somehow you muted yourself. Yes, sir, you're muted.
It's about 1 million miles from the ground, and it's orbiting a location in space that makes it essentially fixed relative to the Earth. So it's far, far away. It's about the size of a tennis court, and it's basically a giant heat sensor. So what it's doing is picking up infrared or heat radiation from the universe, and to do that, it has to be extremely sensitive. So in order to pick up these minute traces of heat that are floating around in the universe since it started with the Big Bang, the James Webb telescope is super cool to a very cold temperature, several hundred degrees below zero. On the other hand, part of it is facing the sun, which is several hundred degrees above zero. So to make sure it can function in both those environments, it has a heat shield, has a shield that shields the heat from the cold side, and the cold side is where the telescope is, and it's able to pick up faint traces of heat from various sources, such as galaxies and other things in the universe. That's what the James Webb Telescope is, and by the results coming in now, it's living up to be truly spectacular. This doesn't come cheap; it's about $10 billion. So that's roughly what it is, and it took many years, roughly 20 years, to produce this telescope and launch it safely. We have a really exciting panel today. Really exciting panel. And we have a set of topics. So one of the panelists is Dr. James Green from NASA headquarters. Dr. Green was the chief scientist of NASA for a number of years. He was also director of planetary exploration. Dr. Green has been with NASA for about 42 years, so he has a lot of experience with the agency, and he's currently a senior advisor at NASA headquarters. He'll be talking in the first topic I'll bring up on life in the universe. Now, before I go there, I want to introduce another panelist. He is his name is Professor Michael Strauss. He is from Princeton University, and he's chairman of the astrophysics department at Princeton University, an incredible department in the world in astrophysics. And he'll be talking about several topics. One will be the early universe and galaxy formation, which is going to be the second topic we'll discuss. And he's also going to talk about the Big Bang and dark matter, and that's going to be the third topic that we're going to be bringing up. I'm also on the panel, and I'll be on the third topic discussing dark matter. And finally, we have a fourth topic on how mathematics can be used to help interpret results from the James Webb Telescope. And Professor Marian Gidea will be leading that session, and I'll be in that session as well. So those are the four sessions. And what I'd like to do is start right in where Jim, Dr. Green, is going to talk about life in the universe.
Well, thanks so very much, Ed. I really appreciate the opportunity to spend a little time talking about what we're finding out in the solar system and how we're using that to find other solar systems throughout the galaxy as best we can with some of the fantastic things. And then, of course, leading up to what is the next series of challenges that we're tackling using the James Webb Space Telescope. Well, let me show a few slides, if I may. I'll share my screen. And I'd like to start out by talking about what we know about our planets. For instance, today, we know that Venus is very hot and Mars is very cold. The Earth is teeming with life. But what we really want to understand is not just the second that we are here today, but what happened in the past with these planets. What are their evolution? It also is important to understand how they will evolve into the future. Well, we now know from a variety of satellite observations that Venus has lost an enormous amount of water. In fact, here is a cloud penetrating radar image of Venus where we see the reds are highlands and the blues are lowlands, has no water on the surface, and it's incredibly hot. It's hot enough to melt lead because it has a runaway greenhouse effect going on. So it's more than 700 degrees Fahrenheit on the surface. But if we, in our computer models, take the amount of water that we believe that Venus has lost over its history and put it on the planet, we get a much different view. And then we run our models, and here is Venus, well in the past, with the water that we believe it's lost. And what happens, clouds form right in this particular region that help reflect the sunlight, that moderate the Venus's climate. that allows it to be a blue planet. So this is a brand new set of observations that over the last several years that are emerging that tells us that it's only been within the last 800 million years that Venus has moved away from being a blue planet, in other words, an ocean world, into the hot, tremendously dry world that it is today. This means that Venus may have had life in its past. Well, today here on Earth, we have extensive life everywhere. It is a beautiful blue planet. We all marvel at these fabulous observations that we see from space of the Earth in the void, so to speak, of the darkness of space. But of course, space is really quite active with a lot of energy from the sun that comes to us in light, some of which we can see, some of which we cannot see. And we need telescopes to be able to look at the Earth and many other bodies at wavelengths we don't see. Well, in a similar manner, one of the sets of observations that we can make here on Earth can tell us about the history of the Earth, the history of our climate. And in fact, what we've been doing is methodically going back in time, trying to uncover what the atmospheric spectra would be like. In other words, what would be the major components of our atmosphere? How has it changed over time? What would be, some of the minor components? And as you can see in these three spectra, and the spectra, of course, is an intensity in the y-axis, and then the wavelength that shows these dips from the line that you see in each of them, which indicates certain types of compositional information in these atmospheres. This is incredibly important to do because we want to understand not only how the Earth has evolved over time, but also be able to predict its future. That's what's going to enable us to, we think, maintain life on this beautiful blue planet. Well, as we move out in the solar system, Mars was also, we believe, a blue planet in the past. We have rovers, we have orbiters, we have all sorts of information that tells us that minerals that have been made on the surface could have only been made in the interaction of water. And so we now know that the past of Mars was also that Mars was a blue planet. In fact, 2/3 of its northern hemisphere was underwater, and a significant amount of water, more than a mile deep in some places. But over time, it went through climate change. It lost its magnetic field, which was protecting the body from severe solar interactions, because the sun generates this huge wind that is interacting with atmospheres, in particular those atmospheres that don't have magnetic fields. And of course, we now believe that the aridness of Mars today is because it lost its water. It broke that cycle of evaporation, transport, and then rain, and lost it into space. So once again, we now know much more about the history of this beautiful planet. So that means the three terrestrial planets, Venus, Earth, and Mars, started out being blue planets, and they have evolved very differently. Well, in the outer reaches of our solar system, what is the possibilities that we might find life? Well, planetary scientists have become incredibly surprised by the concept that some of the moons, particularly these moons from Jupiter called the Galilean Moons, may actually harbor life. Now, how is that possible? All four of these moons, Io, Europa, Ganymede, and Callisto, were made at the same time. And yet you can't find any craters, or only a handful of craters on Europa. And yet Callisto is full of craters. So why is such a difference? Well, we believe that these moons are receiving different types of heat, tidal forces from the planet Jupiter because of their distance from Jupiter, Io being the closest, Io receiving an enormous amount of tidal forces generating the heat that melts in the interior, that explodes on the surface with volcanoes. Europa has an icy shell, unlike Io, who dissipated its icy shell a long time ago. Europa is just in perfect balance. It has an icy shell, and underneath that icy shell, it has an enormous amount of water. And here is some of the latest observations on Io. And what we're looking at Io is in the infrared, and each of these really huge red dots on this body, this moon that's about the size of our own moon, are volcanoes. Io is the most volcanic active body in the solar system. But what about Europa? As we look at it much more carefully, we believe underneath this icy crust is a liquid ocean. That tidal forces from Jupiter are just enough to melt aspects of this icy crust, creating this ocean, this water that's interfaced with soils, with the rocky ocean bottom on Europa, and that the amount of water that Europa has may be twice that of our own Earth. So we think Europa may have all the right stuff for us to be able to go with some of our satellites in the future. Here's a Clipper mission, we call it, that's going to be flying by many times Europa in a pseudo orbit that will enable us to really tease apart the thickness of that ice and give us more information about its potential habitability. Well, this is just a smattering of information about our own solar system. What's happened over the last several decades has been a huge step forward in looking for planets around other stars. In other words, other solar systems. And Kepler, which has done a fabulous job of doing that, has discovered on the order of 4,000 or 5,000 planets. Now, this is a bar chart, a histogram, if you will, where you have the number of planets and then the size of the planets. Now, I always thought, well, you know, what we should find is all these Jupiters out there. Well, it turns out that's not the case. In fact, the most populous planet orbiting stars in our galaxy aren't Jupiter-sized, but they're more Neptune-sized. And we call them super Earths or mini Neptunes. Now, what's really exciting about these planets are they may have oceans, they may have huge atmospheres, they may be really having the right kind of conditions to really harbor life. So what's our next step? Well, that next step is really JWST. Here's where we're going from detecting exoplanets, where Kepler has told us that there are more planets orbiting stars than there are stars in our galaxy. And now we're moving into more of a detailed understanding of these planets by looking at the spectra of their atmospheres. Now, as we all know, Webb has just come online and has made some exciting discoveries. And in fact, in this particular spectrum, we see that in the atmosphere of this very large exoplanet, this is about the size of Jupiter. So we're tackling some of these big planets first. We see in the atmosphere spectra of water. We also find that there is, and this is a new observation, carbon dioxide in some of these planetary atmospheres. Well, this is just the start as we begin that process of really interrogating other planets and comparing those spectra to Earth, not only today's Earth, but in the past. As we said, we understand much more about the evolution of our own Earth's atmosphere. And also, when we see Earth-sized planets, are they Venus-like, are they Mars-like, or are they Earth-like? And Webb will help tease that apart. So it's a tremendous opportunity for us to really look for signs of life in the universe. So Ed, Thank you for the opportunity to talk just very briefly about some of these exciting discoveries culminating with the launch and initial observations of the JWST telescope.
Well, geez, Jim, that was just fabulous. Really exciting to be sure. One question that comes to mind that I have is, what do you think there are signs you can look for in the atmospheres of any of these exoplanets where you might be able to deduce there's actual civilization there? Is that possible? What do you think?
Well, there's a lot of discussion about looking for techno signatures.
Okay.
All right, so what are the technologies we're talking about? Well, Earth went through a time period where we were generating a variety of chemicals that were affecting our atmosphere, such as the destruction of our ozone. This is CFCs, carbon or fluorocarbons. And indeed, we might be able to see some sort of trace gases in some of the planets. I'll have to warn everybody, JWST is not designed to do that at an extent that we could really interrogate Earth-sized planets, but begins the process of really allowing us to tease apart atmospheres of these larger planets. And hopefully we might even be able to see some things in the atmospheres of super Earths that will be really exciting. So we're just starting that process. So anything might be possible in that area, Ed.
That's really cool. Well, thank you very much. Really amazing, Jim. So I think we should move on to the next exciting topic. And this topic is the early universe and galaxy formation and how that might be influenced by observations of the JWST telescope. And for that is Professor Michael Strauss of Princeton University. Michael?
Okay, well, thank you. First of all, thank you everybody for coming. Thank you to Yeshiva University for hosting this. As Jim just said, it's us astronomers love to talk about our stuff, and so as you can hear from Jim's enthusiasm and hopefully from mine as well, we're very excited by this. So Jim has been focused on our own solar system and then planets within our own Milky Way galaxy. I'm going to take us back much further, and I'm going to talk about some of the most distant objects in the universe. And it's important to remember that when we're looking at very distant galaxies, which is what will be the subject of what I'm going to discuss, when we're looking at distant objects, we're looking not just a great distance, but we're also looking back in time. And the reason is because the light that we're seeing from those distant objects has taken a very long time to reach us. So if your friend is sitting across the table 5 feet away, it takes 5 nanoseconds, 5 billionths of a second for the light from them to reach you. So you're seeing them with a time lag of about 5 nanoseconds. If you're looking at Jupiter, for example, that time lag is a few hours. But if you're looking at a galaxy that's 1 billion light years away, well, then it's about that we're seeing that galaxy not as it is today, but 1 billion years ago. And this becomes particularly interesting because, as Ed has already hinted at, the universe started in a Big Bang, and we actually know from a variety of different measurements how long ago that was, with pretty good accuracy, about 13.8 billion years ago. And that's a number that's worth remembering, 13.8 billion years ago. And the universe started in a very hot and dense state and has been expanding ever since. And somewhere along the line, galaxies like our own Milky Way galaxy and the stars in them formed. And one of the big questions in our field is how did that happen? What was the process? When did it happen? Did it happen the same for all the galaxies? Well, probably not. It's an ongoing process, but how can we study that? So to answer that question, what we want to do is to look for the most distant galaxies, because those are the galaxies that are furthest back in time to that time when this was all just getting started. Sometimes when you see the headlines in this, they talk about the astronomers have just found the oldest galaxy in the universe. You'll see headlines along those lines. It's actually, they've got it exactly backwards, because what you're seeing is those galaxies from when the universe was very young, and you're seeing them when those galaxies were very young. So in fact, what we're seeing, whenever you see the headline, oldest galaxy in the universe discovered, just switch that in your mind and realize that in fact, they're talking about the youngest galaxies. So distant galaxies, you will not be surprised, tend to be very faint and therefore require big telescopes. But there's another challenge, which is that the universe is expanding. And in fact, the observations of the expansion is how we know that the universe started at a Big Bang 13.8 billion years ago. That expansion, one of the effects of the expansion, one of the direct ways that we measure that expansion, in fact, is that the light that we see, like the spectra that Jim was showing, is shifted. And what we call it is shifted to longer wavelengths, to red wavelengths. We call it the red shift. We tend to call things as we see them in astronomy. The red shift caused by the expansion of the universe causes the light of a galaxy to be shifted from visible light that our ground-based telescopes are particularly sensitive to infrared light, the heat wavelengths that Ed was making reference to. So in order to really study these in detail, what you need is a big telescope, so you have the sensitivity, but one that's sensitive in infrared wavelengths. And for that, what you really need to do is get above the Earth's atmosphere. The Earth's atmosphere is not well suited to observe those longer wavelengths. So that is what the James Webb Space Telescope is designed to do. It's designed to do a variety of things, but this in particular, it's particularly good at. So with that, we need some eye candy to put this into perspective. Let's go ahead. I think you should all be able to see that there, if I can. So what we're looking at is actually the first public image that was released, actually not by NASA, but by Joe Biden in a press conference the day he scooped NASA by one day. It was really a little amusing. And what you see here is an area of sky, and I'm going to spend a little time on this because there's a lot going on in this picture. An area of sky that was observed with the James Webb Space Telescope with far greater sensitivity than was before. The James Webb Space Telescope is in many ways the successor to the Hubble Space Telescope, which, as Ed was remarking, has been and continues to be an absolute powerhouse in astronomy. But the James Webb Space Telescope is much larger, therefore more sensitive, and particularly well designed to observe at infrared wavelengths. And so it's particularly sensitive to those high redshift, distant, early, young galaxies, and not old, young galaxies. So this is an area of sky where the James Webb Space Telescope exposed for 12 hours, half a day, in several different filters. And there's a lot going on in this picture. One of the things that is worth remarking and is always an issue when one is looking at astronomical images like this is that we're seeing what we see when we take a picture of the sky is we see the nearby objects and the distant objects and everything in between all as appearing like on a single two-dimensional piece of paper. So the great challenge is figuring out what's nearby and what's far away and sorting it out. So let's just spend a little bit of time there. For example, if you see my cursor here, this is a bright star. Here's another star, stars. You can see various stars sprinkled around. Those are stars within our own Milky Way galaxy. They're interesting in their own right, but not the story that we have here. The next thing that you see is a cluster of galaxies, which mostly appear white in this image. There's a big galaxy in the middle and fainter galaxies. Those galaxies are all at a distance, and I should have looked up the number, but it's at something like about 4 billion light years away, something like that. So we're seeing these galaxies as they were 4 billion years ago. Now, again, 4 billion years ago compared to that 13.8 billion years. So these galaxies are almost as old as galaxies that are today. They're not, they're a little bit younger. But then you'll see, mostly appearing in somewhat orange here, a variety of galaxies that are quite a bit more distant here. And we'll come back, because we'll come back to this dark matter story about why they have these funny shapes. You'll notice that there's a pattern of structures here. We'll come back to that. But what I'm going to do right now is jump ahead to this picture. Here, this is just a graphic that was produced by the Webb folks. In this field, there are 4 incredibly faint galaxies. You can barely see them. There's zoom ins here, so you can see they look like rather uninteresting blobby things. And what they are much more distant galaxies. Indeed, each of one of them is labeled with the look back time. That is how many billions of years that light has been traveling to reach us. And here's one that's 11.3 billion years, and 12.6 billion years, and 13.0 billion years, and 13.1 billion years. Remember that you're comparing that to the 13.8 billion years of since the Big Bang, which is to say this galaxy, we're seeing it only 700 million years after the Big Bang, which is really a short amount of time when you're an astronomer. And so I should mention the way that you measure this is for each of these galaxies, you can actually measure the spectrum. It's exactly analogous to what Jim was talking about. And by measuring these various features, and I don't have time to describe them in detail, the amount of shift translates directly into these ages that we're talking about. So what we're doing, and one of the goals of James Webb is to study these earliest galaxies. I mean, James Webb has already broken the record now several times over of the most distant galaxies, and therefore the youngest, earliest galaxies in the universe's history. And what we're now learning is, what are their properties? If you look at these, and if you're used to looking at pictures of galaxies, you'll notice they don't look like what normal galaxies are supposed to look like, because galaxies have changed, they've evolved. We're seeing baby pictures of galaxies as opposed to the mature structures that we see today. So this is one of the key themes, and as Jim emphasized, JWST, we're just seeing the very first images. It's been in operation for, what is it, 2 months or so. It's going to go on for 20 years. So trying to anticipate what the discoveries will be a challenge, and very exciting indeed. What I'm going to do now, Ed, if it's okay, is that switch to our next theme, where I'm going to use the same pictures and talk a little bit about dark matter and related things. Should I go ahead and do so?
Let's see.
Should we pause
Well,
for a little
you still
discussion?
have time. You still have time in this particular topic here if you want to go on a little bit. Unless if you want to phase into the next topic.
It sort of naturally goes on. So why don't
Okay,
if
why don't
it's
you phase
okay, I will
into
just
that?
go ahead and jump. So let's go back to this image, and I wanted to talk a little bit about these distorted galaxy shapes. So one of the things that you'll see if you look carefully is that that some of the galaxies look rather weird in a variety of ways. If you can see my cursor, I don't know if you can see these galaxies that are all elongated and sort of looking like they're arced around that central big galaxy. Let's zoom in on one of those. There's this orange blob that one sees that's sort of hugging this compact galaxy over here. What's happening here is that the light from that distant galaxy, again, remember, and always when we're looking at these pictures, we're seeing relatively nearby galaxies. Well, we see a bright nearby star, nearby galaxies, further away galaxies, and they're all appear to be projected onto two dimensions. But there's a third dimension that's not immediately visually apparent here. And what's happening here is that distant galaxy, the light from it is getting distorted by the mass of the foreground galaxy. This is an effect that is predicted and was predicted by Albert Einstein's theory of general relativity, where you may have heard the phrase that in general relativity warps space-time. It distorts space-time. And that sounds like an abstract and weird notion, but we're actually seeing that visually happening here. That distortion is taking the image of an otherwise perfectly respectable and ordinary galaxy and distorting it very much. And indeed, the mathematics is really very similar to a funhouse mirror, which is taking that image and stretching it out into this funny line that you see here. And if you look carefully at these images, you can see similarly stretched out images all over the place. These streaks and lines that are appearing are a direct effect and direct demonstration of Einstein's theory of general relativity. And so when people say distortion of space-time, what does that mean? Well, we're basically seeing that directly here, which is very cool. But it gets better than that, because you can look at an image like this, and in some cases there's a distortion of a background galaxy from a foreground galaxy, like the one that we were focused on before. But you can see some distortions that are not sort of hugging a foreground galaxy at all. And what's happening there is we're actually learning about the dark matter in the foreground galaxies. What's going on here is we're looking at a cluster of galaxies. There's this bright galaxy, and there's a variety of other galaxies here. But those galaxies, the light that we're seeing there, represent roughly 10% of the full mass of clusters, and all the rest is dark matter. You say, I don't see any dark matter. Well, that's why we call it dark matter. It means that it's invisible. It does not emit light, and that's why we give it the name dark matter. We don't know really what it is, but we do know how much there is, and we can measure that directly by looking at this gravitational lensing, this distortion of the galaxies here. And so with an image like this, we can do, there's a huge range of different science from a single image like this. I've already talked about those distant galaxies there and learning about the very early universe, but we're also learning about how much dark matter there is in this cluster of galaxies. And we can study that whole question in gory detail. And those colleagues of ours who like stars will say, "Ooh, I like these stars. I want to go study them as well." And they get them, as it were, for free together with this image. One of the things that James Webb is planning to do, just as the Hubble Space Telescope is doing, is that all the images, there's a competitive process of which images will be taken, and the scientists who do that have a wonderful opportunity to analyze the data and write scientific papers. But then these images, the data are made completely public for anybody to use. And without Jim was just, when we were talking about this before, was reminding us that with the Hubble Space Telescope, after the fact analysis of the archival data from the Hubble Space Telescope has yielded more scientific papers than the original proposals. And that will certainly be the case for James Webb Space Telescope as well. So, I think already 30 or 40 papers have been written just on this one image alone, doing all kinds of different analyses of the dark matter of the distant galaxies and so on and so forth. This is a tremendous opportunity for us all to explore this universe. Ed, I'm probably about out of time. I don't know if I should stop here or. And I think you want to talk further about the dark matter question.
For the topic that you were in initially was the early universe galaxy formation, which you've done the time on that.
Yeah.
And you've been in the dark matter now on the third topic, and yes. You have another about 2 minutes more on that, and then I would join in with.
Okay, well, let me just a little bit more eye candy if I've got 2 minutes. Okay. This is actually back to galaxies, and it's not directly focused on the dark matter. Here's one of the beautiful pictures that also that was part of the early set of images that JWST produced. These are galaxies much nearer by. Much more mature galaxies. There's if you count carefully, there are 5 bright galaxies. 1, 2, 3. Notice these 2 are very close to each other. 4, 5. These 4 galaxies. This is called Stephan's quintet, named after some astronomer named.
Michael, we're not seeing it on the screen.
Oh, you're not?
No.
Really? Huh. I have no idea why not. That's strange.
Perhaps reshare your screen.
Seeing the
Can
initial
you see it?
picture.
Are you still seeing the initial picture? Oh, I was pointing at the wrong one. There we are. Now are you seeing it?
Yes, that's great. Thank you.
Okay. I was okay. Sorry about that. Thank you. So you see five galaxies, 1, 2, 3, 4, and a fifth one over here. These four galaxies are actually all at the same distance, and this galaxy, by coincidence, happens to be a nearer galaxy that just is projected along the line of sight. But what's particularly beautiful here is one of the things that galaxies do is they bump into each other, and you can see that in the process of bumping into each other, new stars form, the gas is excited in all kinds of ways, and the James Webb Space Telescope is particularly sensitive at picking up some of the effects of this, and these beautiful regions, all these orange regions that one sees here when seeing dust that's heated up by star formation. And in the background, you see many hundreds and indeed thousands of much more distant galaxies that also appear in the same image. And I think with that, I am out of time, so I will stop and let Ed take over from here.
Well, Michael, that is just amazing. I have a quick question for you. You said that image that one that Joe Biden presented.
Yes.
Now he's an astrophysicist.
Yeah.
You said that was a number of hours of view time to get that, right?
That's right.
So my question is, how in theory, how long could they take a view for? I mean, and what would that imply? In other words, if you could look for like a week or two, what would that imply?
Well, I don't know. I don't think anyone has tried yet. Actually, Jim probably has a better is closer to the action there, may have an answer. I mean, well, I mean, there's a variety of different ways to take observations with James Webb Space Telescope. One can observe at multiple different filters, which gives you those beautiful colors that you've seen. And, one of the jobs of an astronomer who's requesting time on the James Webb Space Telescope is to figure out how to make an optimal balance between those different filters, and maybe to measure some spectra, which can take time to figure out exactly what's going on. I mean, a question is, how faint can you go? I'm just rephrasing your question.
Yeah.
What are the smallest, faintest, most distant galaxies that one can possibly see? I think people are going to try to push the limits. Whenever one has a new wonderful tool like the James Webb Space Telescope, one looks for one first does the straightforward things, and then you go and start doing the long exposures and try to push it to its technological limits. So that was a long answer to say that I'm not sure we'll know, but we're going to find out.
Is Princeton involved in any of that?
Yeah, I'm involved. I mean, many of our astronomers at Princeton, including myself, are working on a variety of different projects with James Webb Space Telescope. I'm involved in studying supermassive black holes that live in the centers of these galaxies, and trying to understand when those formed, and again trying to push to the most distant objects to ask the question, let's go find the youngest supermassive black holes there and try to understand that.
So if I may ask a follow-up question, so what is the best hope to go as closely to the Big Bang as possible? So is there any physics limit that prevents us to say we cannot go closer than
so for James Webb Space Telescope, what you're sensitive to is light from stars. That's a galaxy is basically made of stars, and you're looking for that starlight. So in order to see anything, the stars have to have formed. That is, if you push back far enough to large enough distance, you're going back to a time when stars have not yet formed, and then there's, by definition, nothing to see, at least by that. And one of the questions is where is that boundary? We saw a galaxy there was one galaxy with a distance of 13.1 billion a light travel time of 13.1 billion years. There's been a few claims from that same image of objects that were going to about 13.4. And so you think, boy, those are impressively big numbers, getting awfully close to 13.8, which is indeed the absolute limit. And somewhere between 13.4 and 13.8 is when the first galaxies formed. And that is one of the big questions. When did it form?
Thank you so much. Fabulous. I mean, really exciting. This telescope is, like you said, it's only just started, and look what's happening already.
Yeah.
So the other part of this topic, number 3, it's on Big Bang and dark matter, and I have allocated myself for 5 minutes for this. And after what Michael said, there's not much I can really say here. However, what I'd like to do is just comment for the people out there. We're using the word dark matter a lot, and that says many people don't even know what dark matter is. But I just want to sort of talk about that because it's a mysterious word. To astronomers, it's second nature to talk about it. But but if you're not in the field of astronomy, you'd probably say, well, what the heck is dark matter? What is it? And it has a very interesting history. And what I'd like to do is talk about that for a couple of minutes and then talk about maybe what James Webb could do. That would be a paradigm shift, perhaps, and get a little bit science fiction-y here. So basically, the way I like to describe it is if you look at our galaxy, it has roughly, I don't know, Michael would debate this, but it has roughly 100 billion stars in it. And it's got a giant black hole in the middle of it of a few, like tens of millions of solar masses. And everything you can see, the stars, the black hole in the middle, and all of that, if you had a big scale and you got the kilograms of all of that, and you put it on the scale, you'd have a mass, some gigantic mass, which would dwarf your imagination, but it would be a big mass. Now, you can also measure the mass of the galaxy by just observing its rotation. And from the rotation, you get a certain speed. And from that, you can backtrack of how much mass has to be there to make it rotate at that speed. So you put that on a scale on the other side. And in the field of physics and mathematics, you'd like to be able to say, those two things are equal. And not only are they not equal, and this surprises many people, it turns out that in our galaxy, the matter that we are comprised of, which is called baryonic matter, and that comprises the stars and everything else we can see in our galaxy, is only 2%, roughly 2% of what's there. So 98% of all the mass of our galaxy is unaccounted for. Now, this is, to me, absolutely shocking because as I'm looking at you and you're looking at me, in our solar system now, the number's not quite that, it's roughly 50-50, roughly 50% of the dark matter comprises where we are. This means roughly half of the mass is not accounted for. So what I'm hoping with the James telescope, roughly, is that it can with its high resolution, look in our galaxy and see, for example, what's out there that might be causing this. Now, we don't know. There's a number of theories. One theory is that dark matter could be caused by subatomic particles of some type. Another theory is that dark matter could be black holes, smaller black holes. The galaxy could be teeming with them for all we know. There's another theory that our theory of gravity is not correct. And it could maybe, it's called the Mond theory. And I think that's been disproven. But there's a lot of theories floating around, but a very exciting one to me is the idea that it could be mini black holes all around our galaxy. And possibly with the resolution of JWST, these kinds of questions, we would be able to resolve that. And as Michael mentioned, dark matter has gravity on it, just like regular matter does. And when light goes by it, by Einstein's theory of relativity, the light gets bent and things get distorted. And the James Webb telescope might be able to really look at that with a precision we have not been able to see before in our own galaxy. So that's all I wanted to say on that topic. And with that, unless there's any questions from the panel, we can move on to the next topic. Okay. The last topic for this incredibly exciting event, and I'm really sorry it's going so fast. It was made to be an hour for the panel, and I should have made it like 5 or 6 hours, or maybe 10 hours. This is just fantastic. The last topic is a little bit more esoteric, really, but it speaks mainly to the mathematics, and it's entitled "How Mathematics Can Offer Clues as to What Perhaps James Webb is Observing." And to lead this off is Professor Marian Gidea, who has a tremendous amount of experience in dynamical systems, and he's the perfect person to ask, what clues can we get from mathematics?
Thank you very much. So first, because it's an esoteric, more esoteric question, I will start with a more esoteric answer. So I think from James Webb and from other telescopes, what we get is a tremendous amount of data. And we try to understand this data and in mathematics, but also jointly with physics and astronomy. We try to build models. We try to verify these models against data. We try to analyze the models and possibly design new experiments to enhance our understanding of the data. And to give a concrete example, I'm just going to take the opportunity to boast about some of the very recent work of my colleague at Yeshiva University, Dr. Belbruno, joint work with Dr. Green. So it's about the detection of dark matter using measurements performed within our solar system. So basically, they describe some models for the distribution of dark matter in the galaxy. And the question that they pose is that whether they can measure the effect as it acts on objects in our solar system. And two of the objects that they mentioned in their work is, one is the Pioneer 10. So this is a spacecraft that was sent into space. So I hope you see the screen, right?
So yes, we can see it. Yeah, we get, yeah.
Okay, thank you. So this was sent to space like 50 years ago, and it stopped transmitting data maybe 20 years ago. So it ran successfully for 31 years. So, and you see it's very, very far. So it's beyond Pluto. And one of the observed phenomena was what is called Pioneer anomaly, that the actual trajectory deviated from what it was predicted. And one of the questions it was asked in this paper is whether this can be something to do with the effect of dark matter. So it's a very challenging question because there is a competing effect, which is thermal radiation force, which is a force generated by the power generator of the spacecraft. And those two forces, one due to dark matter, the galactic force, which is combined dark matter and usual matter, it's very small, but also the thermal radiation is very small. So these two combined might have an effect, and it would be very nice to measure, to distinguish between these two effects. So another spacecraft, it's New Horizon. So this also was going, it's very, very far. So let's see, so New Horizon, it's also going past the orbit of Pluto. And it's the same question that their paper is asking. So whether the defect in the trajectory of this spacecraft has something to do, or can be used to measure the effect of dark matter at the level of our solar system. So this is an extremely delicate work, and it's extremely innovative. So as far as one can tell, nobody thought about this type of approach before.
No, I don't like. No, I don't like crumbs in my. Huh?
It involves really serious mathematics, in the sense that not only one has to understand the gravitational field of the galaxy, which combines the baryonic matter and the dark matter, but also what is the dynamics of objects like such as spacecraft within our solar system. So, and I think one of the question is maybe these two spacecraft are, it's challenging to actually detect and measure the effect of dark matter using those spacecraft. And I think in the paper, they are proposing that other missions or other type of methods can be designed in order to get more accurate measurements. I think, I don't know if I have another minute or not, so maybe I could just.
So yes, you do. You have
Okay.
a couple more minutes, Marian.
Excellent. So maybe I can just touch briefly on one of the topics that Dr. Green referred early on. So let me. So there are many solar systems out there, and they tell us about what are possible evolutions of a solar system, and they can give us some insight into how our solar system might evolve. And this is a recently discovered solar system. It's called TRAPPIST-1. I like this a lot for mathematical reasons. So this was discovered before the Webb telescope. It consists of 7 planets, and some of these planets are apparently habitable. And the orbits have a very particular characteristic. So they are so-called resonant orbits. So that means that some of these planets get aligned relatively frequently. And this is like in a way, a pocket solar system, because the period of these planets around the star, it's like between 1 day and 18 Earth days. So they go very fast. So it's very instructive to study such systems. So there are questions about whether they are stable. Typically, resonances may lead to instability, but this is a solar system that appears to be stable. And you get also some insights of solar system that may provide a good habitat for life. So apparently some of these planets are likely to do that. So I think I just wanted to illustrate through these 2 concrete examples, way in which mathematics can contribute together with physics and astronomy to a better understanding of some interesting phenomena in space. Thank you.
So I wonder if I could ask a question.
Oh, absolutely, yeah.
Yes, which is you give examples of where mathematics is a wonderful tool to understand physical systems, but I'm interested in the converse, which is cases in which astronomy has informed the mathematics. That is, we've learned new mathematics by studying astronomical or astrophysical situations. And the example that I think of that maybe like that is, again, the distortions of the shapes of galaxies that I've talked about. I mean, the development of general relativity really required and then motivated and a number of new developments in mathematics. And there's still mathematicians who are continuing to explore all the mathematical consequences of Einstein's theory. I wonder if you could comment further on that.
The only comment I can make is that I can't agree more. So I think, yes, there are lots of mathematical ideas in general relativity and in understanding the structure of space and of matter, in which the astronomy has led to new fields of mathematics. where one of them that comes to mind is string theory. So it's a very it's a sophisticated theory that it's like the theory of everything, that is trying to provide unification of all the forces that exist. But I think there are many others. So a lot of, let's say, a lot of geometry, non-Riemannian geometry, non-Riemannian geometries are motivated by astronomy and astrophysics, as far as I can tell.
Thank you, Marian.
Yeah,
Any other
we're
questions?
Marian.
Selma, do you have a question for Marian?
I wanted to draw Marian's attention to a comment and a question in the chat room.
Okay. Thank you. Yeah, so I think, yes, we got a comment from the audience. So I'm going to just read. If memory serves, that's why Newton and Leibniz developed calculus to explain what they are seeing with their eyes. Thank you for this comment.
I think that is correct, as far as I know that, I mean, Newton was developing the physics and developing the mathematics in parallel with each other. I mean, Leibniz was, I don't know as much about Leibniz, but Newton really had to develop the two in parallel with each other. And the physics informed the mathematics, and the mathematics informed the physics. And that comment is absolutely spot on.
Mm-hmm. Yeah, interesting. Yeah, Newton, incredible, first law of gravity, laws of physics, calculus.
Yeah, and many other things beside.
All from an apple falling from a tree.
Well, among other things, yes.
Okay, but so before we go to the questions from the audience, I'll just close out this last session here on mathematics. I think many things have been covered by Marian and also by Michael. And all I wanted to add was sort of a different view that I like to take on it. The Big Bang is a process that we don't know what it is. In fact, we don't have the slightest idea what it is. And it's an event that happened a long time ago, and suddenly a lot of energy came out seemingly from nowhere. And our universe, as we're observing it, was made. Now, because we don't know what it is, I'm sort of one of these people that's looking for some game changer results from James Webb. And one of them is that, as Michael was talking about, that magic number 13.8, wouldn't it be something if an object was observed that was actually very close to that, closer to what we think it should be? And that would really force us to rethink the Big Bang phenomenon. I just wanted to mention it by way of mathematics that there is a way to study the Big Bang that could work in concert with some observations, and that's a field of mathematics within the field of dynamical systems, which Marian Gidea knows very well, called regularization theory. It's in the field of celestial mechanics, and it's a way to take a very nasty state like the Big Bang, which has a lot of energy and a lot of properties which make the Einstein equations not defined, and therefore you seemingly can't study them at that time or at that epoch where that would occur. You can actually do a change of setting and make it so you can actually observe it. That's called a regularization. And by looking at a regularization, you can get a sense of if there is a Big Bang and it has formed due to a converging solution of Einstein's field equations, then what we'd expect to see there. And if you don't see anything there, then can you adapt the mathematics to explain that? And there are other fields of mathematics which look at that problem using string theory, which you've all heard about, and some other fields. So that's an area where there could be an interesting interplay between advanced mathematics, string theory, dynamical systems, regularization theory, and what the James Webb might observe about the Big Bang. So that's all I wanted to say. Throw that out there for a discussion by the panel. And after that, we'd open it up. Marian will open it up to questions for the audience, which I'm probably dying to ask some questions. Any questions on the panel or any discussion about that last topic in the mathematics?
Maybe I can ask a quick question. So is this regularization applied to Big Bang singularity? Can it provide any insights into the theory of Big Crunch? So whether the universe before the Big Bang was first squishing and then exploded, and it may go into cycles.
Absolutely. I've worked in that area, and there's a number of results, but one of the cleanest results is a result I came up with Bing-Khan Zui, a student of Professor Paul Steinhardt at Princeton University. And by using this regularization, you can show that there could have been a previous universe that squished down to the Big Bang state and made the Big Bang to make our universe. But that process could happen in a smooth fashion, in a continuous fashion. And it turns out there's a wild condition for that. And the condition is that a key parameter in the problem has to be a relative prime number. And that parameter is called the equation of state. And it has to do with the ratio of pressures, which I don't want to get into. But if that particular parameter is a relative prime number, which belongs in a math course to discuss that, it turns out that you can in fact have that. You can go from Big Crunch in a previous universe to a big expansion in ours. And with the big expansion, maybe we should stop it there and open it up for questions.
So I'm going to read some of the questions in no particular order, how they're. So one of the question is, what are the dates of the first stars relative to the dates of the first galaxies?
Maybe I can try to take a stab at that. So one of the challenges, an entire galaxy, as Ed pointed out in his presentation, a galaxy a big galaxy like our own consists of 100 billion stars. So, and you saw in those pictures that I was showing that individual galaxies can be quite faint. So a single star at the enormous distances that we were talking about, or at the very early universe, are not going to be individually observable. I mean, we would love to be able to pick out individual stars only a few 100 million years after the Big Bang. Even the James Webb Space Telescope can't do that, at least not straightforwardly, although people have some clever ideas that would take us a little far afield about how one might do that. So here's another way to phrase this question, which I will not answer. Which came first? Did a galaxy form first and then stars formed within it? Or did the stars form first and then they clumped together to make a galaxy? We're pretty sure it's the former, but it sure be nice to be able to actually observe the process and see it happening. In our own Milky Way galaxy, for example, which has been around for a long time, stars continue to form. The Milky Way probably formed early in the universe of 13 billion years ago. Our own sun formed 4.5 billion years ago. So our sun is relatively young. The sun and therefore the planets around it are relatively young compared to the galaxy overall. But how did this whole process start? Which is another way to ask the question that you had posed. We don't know. We will certainly get clues to this by studying what the nature of the galaxies that we can see at these very great distances of this very early epoch in the history of the universe.
Thank you. So another question that I'm going to pick from the list is, I think it's for Dr. Green. Exactly how can we compute the water volume Venus had?
Mm-hmm.
Yeah, so this is a tricky measurement. It's called the D to H ratio. And what it means is deuterium to hydrogen. So what is hydrogen? Well, it is one proton with an electron orbiting, and deuterium is one proton with a neutron in the nucleus and an electron orbiting. So in other words, it's still one proton, which makes it a hydrogen. Now, deuterium is found in nature, and you can go out to the ocean, scoop up some water, and then begin to look at the hydrogen that is connected with the oxygen that make up the water, and count the hydrogens and the deuteriums, okay? And then form a ratio. And so the assumption is the ratio of D to H we have in our ocean must have been what Mars had, must have been what Venus had, but that ratio changed. So the trick then is, when we make a measurement on Venus, you know, even though the water is gone, but not all the water is gone, we can indeed create this ratio. We can make this measurement of D, and we can make this measurement spectrally of H, and we can get the ratio, and we see it's so much different than that from the Earth. So therefore, to make that ratio we see on Venus the same as Earth, we add the water back, and we find out it's an enormous amount of water. Now, how did this ratio get so goofed up? Well, it got goofed up because hydrogen is lighter than deuterium. Well, it's lighter by the mass of a neutron. And so when water evaporates, the water vapor that contains hydrogen will be able to go further up into the atmosphere. And once again, as I talked about how changes occur in our upper atmosphere that strip away the water, eventually then will strip away the hydrogen rather than the deuterium. And so that's what gets the ratio all goofed up. And that's how we make that measurement.
Thank you very much. So here is another question. Since dark matter exhibits gravity, why does it stay in the outer regions and not clump up in some kind of visible objects?
Do you want to take that, or should I?
Could you read that again, Marian?
I'll read it again. Since dark matter exhibits gravity, why does it stay in the outer regions and not clump up in some kind of visible objects?
Okay, I can take a very superficial stab, and then you can do a better job, Michael.
Okay. Go ahead, go for it.
It seems like a dark matter does not, like, for example, if you take a lot of regular baryonic matter and you have it floating around in space, gravity will force it to squeeze down, and you can get things, for example, with so much squeezing, for example, like a black hole. But dark matter is attracted in our galaxy. However, it doesn't exhibit that same quality. It piles up towards the center, but does not want to go more than a certain density. And so there's a property where the density is sort of restricted towards the middle, and it has a mass density distribution which just decreases as you go out. It's uniform in all directions according to our models. That's all I can say. Michael?
Yeah. So one of the challenges, as Ed is saying, he's making the distinction between dark matter, baryonic matter, and now I'm just repeating what Ed had said. The baryonic matter is the stuff that you and I are made of. It's ordinary atoms, from hydrogen up to uranium and everything else. The stuff that we're familiar with. Dark matter, even though we don't know what it is, we know it's not baryonic matter. And whatever it is, its defining characteristic is that it doesn't emit light. So you can squeeze it in various ways, but if there are no baryons, ordinary atomic matter around, it will never form into stars, which is the stuff that we know that our telescopes can see, or planets for that matter. So in some sense, it's a defining characteristic of dark matter. It's empirically shown that this stuff isn't visible. We infer its existence, as I was describing, by the gravitational lensing effect, those distortions of the galaxies, or by the rotation of galaxies, as Ed was describing. So we see its gravitational effect on things, but we do not see it giving off any light. And that is sort of it's an empirical statement that we don't see the stuff. And so whatever it's made of, it never gives off light. It can, in principle, it could even in principle clump into a black hole, but we're not going to see it.
And we really don't know, right? This is
No, we really don't know. I mean, we give it this name, and we actually can measure. So what do we know? We do know that it's there. We actually know in fair quantitative detail how much there is from measurements like what we were just describing. But the question of what it is, well, we know what it isn't. It's not ordinary matter. It's not baryonic matter. And so then you say, okay, if it's not that, then what is it? And then the theoretical astrophysicists have a field day and invent all kinds of wonderful ideas of what it might possibly be. But we do not have a clean answer to this question. It's one of the big questions in our field.
Another interesting question is life in the universe necessarily carbon-based or water-dependent?
Well, that's a question for Jim.
Yeah, let me take a hack at that. So at the root of the answer to that, it really starts with the definition of what is life. And I have to tell you, we struggled with that a little bit. So we had our astrobiologists get together and meet and argue and really I wanted them, when I was head of planetary, to be able to come and tell me a definition of life that we could then go out and build instruments and go fly to planets and find it, So give me that definition. So after a couple of years, they came back and said, we've got the definition. And it basically goes like this. Life has three attributes. The first attribute is it metabolizes. Now this is where you bring in a solid with a liquid, and the liquid is a solvent. You then take the material you want out of the solid, that's the food, and then the liquid is used to eliminate waste. So that in essence is the metabolic process, metabolism. So it metabolizes. Second thing is it reproduces. The third thing is it evolves. Now the astrobiologists were absolutely delighted with that, and I have to tell you, I was pretty sad because I can't build an instrument to go make those measurements. All right, we're not flying something that measures evolution on Mars or anything like that. But we can follow the liquid, and on Mars we're following the water. And so that means when we look at exoplanets, we're looking for a liquid. We're looking for, when we see water, we get really excited because we know here on Earth, water is that essential ingredient, is part of the metabolic process. Now that you know that background, here's the answer to the root of your question, and that is, are there other liquids that may be part of a metabolic process for a different type of life? And the answer to that is, we're studying that. We don't know, but we think it's possible. We haven't come up with anything definitive, but I started funding research in that area about 15 years ago. And it started a new field of research these astrobiologists call weird life. Okay, weird life. There's actually now a couple popular books that have come out that talk about what is weird life. It's life like we don't know it. It really is based on that same definition of life, but where a different liquid comes into play. Now, I'll just end with this. Here's the exciting part of that research relative to the solar system that we have today. And that is, we have another body in the solar system that has liquid lakes, rivers, it rains. And that liquid is not water, it's liquid methane. And that body is a moon of Saturn called Titan. And Titan is a huge body that's bigger than the planet Mercury. So we want to go back to Titan because if there's any place in the solar system where we might find life not like us, it would be on that body. Okay.
Thank you so much. I think the time is almost up, but there is one question that I think will allow us to end in a high note. So what is the most exciting picture or discovery that Webb telescope made so far?
Well, I think each of us is going to choose our own favorites. One of the things that I tried to emphasize in my presentation is that, from a single image, there's a huge range of different science that one can do. Astronomers, tend to categorize themselves as those who study galaxies or study stars or study planets or various other things. But we're all interested in everything. And so each of us will choose our favorites. One of the things that astronomers do now is when we write scientific papers, we post them on a website, and we get a daily email saying, "Oh, here are the latest papers that were posted in the last 24 hours." And every day there's another few papers from James Webb Space Telescope. So the data, the fire hose of wonderful results is turning on, and any answer that we give today about what the most exciting image thus far is, it will certainly, tomorrow we'll say, ooh, this one's even better, and we like it even more.
Well, for me, if I may, it's really the Karina Nebula. And if I can, it is absolutely spectacular. If I can share my screen very quickly for those that may not have seen it. Here it is. This is a pretty spectacular image. Yeah, it really is a nursery where stars are being made. So these are the ones that have made their winds. These stellar winds are blowing back some of the gases, concentrating them. New stars are being made in these areas. In fact, there's some things like, some of these stars even have envelopes of material around them where there might even be forming planets, where they're fending off because they have that star now is actually burning creating nuclear energy through what happens in the core, and it generates magnetic fields and does all kinds of stuff and produces heliospheres, we call it, or astrospheres as astronomers call it. And so studying this, I think is really one of the things that I have enjoyed looking at the JWST images. Thank you.
Marian, what about
you? Thank you. So for me, the question that the picture that I like the most is probably the picture that many of the panelists will think is the least exciting. Is the picture of Jupiter. It's a very recent picture of Jupiter.
Yeah, that's stunning.
Gives you a lot of detail about the storms, high atmosphere, and the whole motion at the surface of Jupiter. That I think it's very interesting, and I think for mathematicians who study like fluid dynamics, it has a lot of information that can open up.
It is a stunning image indeed.
It's incredible, yeah. I would have to go with Jim's favorite there. The nebula is amazing. It's amazing. The scale of that is huge too. It's
the scale of that's huge. Yeah.
Thousands of light.
quite the nursery, quite the nursery.
So
I would like to just say to all our participants tonight, thank you so much for tuning in, and our panelists for a stunning series of conversations. I'd like to particularly thank Michael Strauss, and Jim Green for gracing Yeshiva University with their presence. And of course, Ed and Marian, as always, thank you very much. So thank you all. We hope to learn more, and we'll look for your words of wisdom about James Webb Telescope. Thank you.